right, let's put a pin in Chapter 4. Welcome back to Math 111. This is the last section in Chapter 4. This is Section 4.3, and it's all about rational inequalities and applications. And I'm going to focus primarily in this video on applications, and we will, if you guys have any questions, if there are any questions about inequality, please bring them up in class or in a web conference. So for today, for this recording, I'm going to focus on applications because I find those to be the more challenging part of this. So let's start with the box with no top problem. We've got a box that has got a square base. So in other words, the width and the depth are the same. They're both x. And we are constructing this box so that it's got a volume of exactly 1,000 cubic centimeters. What we want to do is we want to express the height in centimeters as a function of the width of the box. And then we want to make sure that we want to look at the x's where our height will be greater than our base dimensions. And then we're going to talk about some end behavior. We're going to express the surface area of the box as a function of that x, and we're going to estimate the dimensions of the box that will minimize the surface area. In other words, what dimension will give us our desired volume with the least amount of material used? And I need to make me a blank slide, so give me just a second here. I need a place to work. Okay, so let's think about our box. We have got a square base. So this is x and this is x. And then it is some h centimeters tall. Jordan. Okay. Almost looks like a box, not really. Okay. Our volume is length times width times height. We also know that our volume is 1,000 cubic centimeters. So that means h is given by 1,000 divided by x squared. And there we go. There is our height as a function of x. This works because our box is a square. That makes it a lot simpler. Okay, so what does that mean? Well, it's a rational function, right? It's going to have a vertical asymptote at 0. Yeah. What else does that mean? So what happens as x gets smaller? Well, we already said that if x gets smaller and smaller and smaller, our box gets bigger. Our box gets taller and taller and taller. Meaning, if we want to maintain our volume and our base gets smaller, our height's got to get bigger. No big surprise there. What happens though as our base gets bigger? In other words, as x goes to infinity, well, same volume, height's got to go down, right? Okay. All right, so now let's talk about the surface area. All right, the surface area of my box, well, it's the area of the bottom, which is x by x, plus 4 times the areas of the sides, which are equal. So 4hx. Well, we've got h as a function of x. So that's going to be 4x squared, or x squared plus 4 times 1,000 divided by x squared times x. So that is x squared plus 4,000 over x. If I combine this into a single rational function, we get that our surface area is going to be x to the third plus 4,000 divided by x. That means we've got a horizontal asymptote. No, we've got a vertical asymptote at x equals 0. We will not have a horizontal asymptote because the degree of my numerator is bigger. We will, though, so as x goes to positive infinity, we're going to approach a quadratic equation. So if we graph this thing, y equals, in parentheses, x to the third plus 4,000 divided by x. Let's graph that. I need to change my window. Let's go from 0 to 50 on my x scale, and from 0 to, we'll go to 10,000, and we will step by thousands. Now let's graph it. Okay, so we can see that there is a minimum surface area. Let's find that. So we're going to use the calc feature, and I can find a minimum. I want my left bound to be something to the left of my minimum. So something over here. Right bound should be somewhere on the right, to the right of my low point, which I really can't see because it's behind my, there we go. And we'll guess somewhere in here. Calculator will search. Calculators being silly. All right. We're going to ignore my calculator because it's obviously malfunctioning. Let's go to Desmos and graph it here. Y equals x to the third plus 4,000 divided by x. Same settings. We'll go from -1 to 50, and from 0 to 10,000, and step by thousands. And we can see the minimum is at about x equals 12.6, 12.5, well, 12.60. So the dimensions that give me a volume of 1,000 cubic centimeters with minimum surface area are 12.60 centimeters on the base, and what would that be? Let's see if my calculator has decided it's going to behave. Nope. It's all right, Desmos will work as a calculator. 1,000 divided by 12.6 squared is 6.30. So my height will be 6.30 centimeters. Notice this is not in the regime where my height is greater than my base. That's okay. Okay, if you have any questions, let me know. So the other thing we want to talk about is proportionality. These are not hard. We tend to overthink these and try to make them harder than they actually are. So let's think about, suppose we've got x, y, and z are variables. Y varies directly with, or sometimes we say y is directly proportional to x if there is a constant k such that y equals kx. All right, here's the thing. That's math speak for saying that if x goes up, y goes up, and that the rate is unchanging. For example, if you are working a job that pays a specific wage per hour, the more hours you work, the more money you make, assuming you never get into overtime. The other way to think of this is for a given year in which the price of wheat is constant, the more bushels you harvest, the more money you get. Okay. There's another kind of proportionality we're going to talk about, which is that y varies inversely with, or we can sometimes say is inversely proportional to x. And that occurs if we can find, if there's some constant such that y equals k divided by x. So the way to think about this is that if x gets bigger, y gets smaller. We can also have joint proportionality. And joint proportionality says that if z varies jointly with or is jointly proportional to x and y, then that just means z is equal to some constant k times x times y. Some examples. Hooke's law is the law that governs springs. The force exerted on a spring is directly proportional to the extension of that spring. Boyles Law, you may remember from chemistry, is that at a constant temperature, the pressure of an ideal gas is inversely proportional to its volume. The way we usually write this in chemistry is that P1 V1 equals P2 V2. Or we say that the pressure is equal to some constant divided by the volume. We kind of talked about this with our box. Volume was constant, which meant, and so as the base got bigger, the height got smaller. So for a constant volume in our box, the height was inversely proportional to the square of the base. Ohm's law. Ohm's law is usually written as V equals IR. So the current through a conductor is directly proportional to the voltage, provided the resistance, and inversely proportional to the resistance. So you can see current and voltage are on opposite sides of the equal sign. That means they are directly proportional to one another. Current and resistance are on the same side of the equal sign. They are inversely proportional to one another. Newton's law of universal gravity. The gravitational force exerted on any two objects is varies directly with the product of the masses and inversely with the square of the distance between their centers. Here is what that means. The gravitational force is equal to some constant times the product of the two masses divided by the square of the distance between them. Varies directly with the product of the two masses, that's m1 times m2, and inversely of the square of the distance between them, that's r squared. Okay. Let's do a Boyles Law example. We've done this experiment. Let's say we did this experiment in a lab. And we got actual data. And we've been told that the pressure should be inversely proportional to the volume. So what that means is that pressure should be equal to some constant divided by volume. Or the other way of writing that is pressure should equal some constant times v to the negative 1 power. So let's do a regression. We could do this with a power regression on our calculator. We can also do this in Desmos. Desmos is going to be easier to see, so let's use Desmos. Let's go ahead and put the data into Desmos. There's a lot of it, so bear with me. 48, 46, 44, 42, 40, 38. How do I know that my volume should be my x's? Well, the problem told me to use volume as the independent variable. That means x's. So now we've got pressure. Screw that one up. Well, this is looking promising. As volume goes down, pressure goes up. Okay, let's reset our graph settings so we can actually see. Oh, we'll take our x-axis from 0 to 0 to 50. And our y-axis from 0 to 120. Okay. That looks like it might work. Let's try a power fit. So let's try y1 is maybe equal to k times x1 to the n power. And my fit tells me that, yes, my n is about 0.99, negative 0.99, so that's negative 1, so k is 1398. So what my Desmos fit told me was that my pressure is equal to 1398 times volume to the negative 1, or 1398 divided by volume. And they do vary inversely. And we have found the constant value. All right. And here is the same thing on your calculator. They used 1400, close enough. I may have had a data entry error. That is it for this last section of Chapter 4. I will talk to you all soon. Have a great day and do good math.